So, welcome all. Today we are going to revise the topic electric potential and capacitance. That is the second chapter. In this chapter, in this lecture, we are going to just revise what is electric potential. So, for understanding electric potential, we need to have an idea regarding what is an electric potential energy. So, we know that electric potential energy is the work done to bring a unit test charge from infinity to a point against the electric field. That means, if suppose the Q charge is there, Q charge is placed at this location, and on the electric field of this Q charge, let P be a point. Let P be a point, and this is at a distance R from the charge. Imagine this is infinity. Imagine this is infinity. And there is a charge Q0 which is at infinity. And I want to bring this Q0 towards the point P. So usually this is a plus charge and this is also a plus charge. So there will be a repulsion. So to overcome that repulsive force, I need to apply a force against that electrostatic force. So I need to do a work in bringing this Q0 charge from infinity to P. So it is difficult to calculate the length measurement in the case of this charge. So it is difficult to calculate the length measurement regarding infinity. So we are considering 2 points, say A and B, which is at a small separation. The distance between Q and A is say X. This is a variable value. And the distance between A and B, it's a small distance taken as dx. Now we are calculating the small work done in moving Q0 from A to B. So what is that work? We know that work dW, small work done dW, is equal to F dot dx. When you expand the dot product, you will get cos theta. Since the angle between this force is electrostatic force and the distance dx, so normally electrostatic force will tend to align the Q0 in the opposite direction because there is a repulsive force. So when expanding, you will get minus F into dx. This F is actually electrostatic force. Therefore, we can write dW is equal to minus 1 by 4 pi epsilon 0 capital Q, Q0 divided by what is, if assume that it is placed at X, so this is X square into dx. Now integrating the expression, W is equal to minus of integral. We need to bring the charge from infinity to P. So infinity to P is at a distance R from Q. Therefore infinity to R, 1 by 4 pi epsilon 0 Q, Q0 into Q divided by X square into dx. On taking all the other terms to the outside part of integration, minus 1 by 4 pi epsilon 0 capital Q, Q0 integral infinity to R, 1 by X square dx. So 1 by X square dx can be integrated by taking the value of X square to numerator. So that will be X raised to minus 2 dx. So W is equal to minus Q0 by 4 pi epsilon 0 infinity to R X raised to minus 2 dx. So on expanding, on integrating this x raised to minus 2, we get x raised to minus 2 plus 1 by minus 2 plus 1. So W will be minus q into q0 divided by 4 pi epsilon 0 after integrating x raised to minus 1 by minus 1. That will be written as minus 1 by x into infinity to r. Now taking upper limit minus lower limit. Upper limit is r, lower limit is infinity. So upper limit minus lower limit, we get W is equal to negative cancels, 1 by 4 pi epsilon 0 q0 divided by r. So this is the expression for work done, and you know that this work done is equal to the electrostatic potential energy. So this is the expression for electrostatic potential energy. Next is electrostatic potential. So electrostatic potential, we already know that this the given expression U is equal to, in the previous session, 1 by 4 pi epsilon 0 q0 divided by r square is electrostatic potential energy. So assume that at every point the electrostatic potential energy can take different values, because from this expression we know that this electrostatic potential energy depends on this charge, the amount of test charge which is bringing. So to avoid this contradiction, we are defining a new term called electric potential. So electric potential at a point is always same. Potential may vary from point to point and it is independent of the test charge. So electric potential V is equal to potential energy per unit test charge. That means you can say that it is the work done in bringing a unit test charge from infinity to a particular point. Or we can write this expression like this also. W by Q0 is equal to potential. So V is equal to, you can say that 1 by 4 pi epsilon 0 Q. This Q is source charge divided by R square. So this is the expression for electric potential at a point.